On this slide, we talk about sheaves of modules. We start with the OX module sheaf F. So OX is some ring, and we are talking about OX module sheaf F. So this is what we need to define: OX module sheaf F. We already know what OX is. So we start with OX as a ringed space. So say U is an open set of this topological space X. This topological space X has structure sheaf OX, and we want to talk about OX module. So you fix an open set, then this F of U, this thing is a OX module. So you see structure sheaf by itself is a OX module. So here we are making it slightly more general. Now this OX module F of U, which is a OX module, should satisfy some restriction map. That is very obvious. So you have this corresponding map. U contains V. You have a map from FU to FV. Similarly, you have this map from OXU to OXV. So by definition, F of U is a OXU module. So this is the definition. F of U is a OXU module. And similarly, F of V is OXV module, but F of V is also OXU module via the map R. So F of V is also OXU module via map R. So let us just show this. So you have A which gets mapped to RA. Pick a function F in F of U. Rho will map it to rho of F. So the restriction mapping would be so we are saying restriction maps are linear. They are linear in the following sense. So you take F in F of U, it gets mapped to rho of F in F of V. So you get rho of F or rho of AF. You take A from OXU. You're talking about module OXU module, so you're multiplying by an element of the OXU ring. So this is equal to RA times rho of F. This is kind of obvious, but that is precisely the OX module sheaf should satisfy. So the simplest example is OXU itself is the OXU module, or you could take direct copies of it. So direct sum of n copies of the structural sheaf OX. So you take a direct sum of n copies. So we are taking this as finite direct sum. N could be 1 also. Simplest example is n is 1. Now we want to define the tensor product. So if F and G are two OX modules, so both F and G are two OX module sheaves, we define tensor product to be the sheaf associated with this tensor product is nothing but the sheaf So this is the sheaf associated with the following pre-sheaf. U is mapped to f of u, tensor it with, because f of u is OXU module, so is g of u is also OXU module, so you tensor over OXU, and this tensor product what you get is also a OX module. So now we have defined what a general OX module sheaf means. So it is nothing but a module over a ring. So that is the basic idea to think about it. There's nothing deep in it, and we have also seen the tensor product. Now we want to talk about sheaves of modules on affine algebraic variety. So obviously the way we want to define module, if we replace the module by structure sheaf itself, we should get precisely the sheaf of regular functions. So it should have some sync with sheaf of regular functions, because the module you could take as OXU itself. So that is the guiding philosophy. So we have to keep in mind the sheaf of regular functions. So you start with the affine algebraic variety. You have a structure sheaf O of V, we have the algebraic set V, and you have to have some module M, and this module is a OV module. So now we define OV module M tilde on open sets UF. So we did the same procedure with structure sheaf. So now we are doing the procedure with OV modules, and here these new modules which we will construct on open sets, we will denote them by M tilde. So open sets are of the form UF, so this will be M tilde. So what is the module on the open set U of F? So this is nothing but MF, that is the module M localized with F, which is nothing but M tensor with so you see the second part O of V, then localized by 1 by F, or localized at F. So you can see it is just a tensoring. And on the entire space you should recover the module you started with, the module M you started with, just like in structure sheaf. So this is just M because M is a OV module. That is pretty much it. So this is just about localizing the module, just like you localize the ring. So to localize a module, you just tensor it with the localized ring. So to understand this, you just need to understand what is the localization of a module. So you first localize the ring, and then you tensor the module with the localized ring. So again, what is the localized module? First thing is you localize the ring. So if M is a R module, you localize the module R, say as RF, and then tensor M with RF, you get a localized module at F. That is it. So now we are just going to write it down. After all, once you do localization, they are fractions. So we will say one fraction, say ms, is same as fraction yt, if there exists. We are introducing this element u, and I'll just say why we introduce it. So the two fractions are equal. So the two fractions m by s and y by t are equal if u times m by s is equal to u times y by t. Yeah, or you just multiply both sides by st and bring everything on the left hand side. Yeah, so why do we introduce u? We introduce u because we are worried about the denominator s or t might become 0 in certain cases, and that might happen if O of v is not an integral domain or M is not torsion free. The second part is M is not torsion free.